Welcome back. Today I want to share some prototype information. So in these videos we've talked about engine performance, cylinder head flow, so on and so forth. A recent series of videos released from Engine Performance Expo. Darren Morgan went in all kinds of details of what he has experienced being a cylinder head manufacturer, porter, designer, so on and so forth. Within the video they talked about two or three different variations of actual engines. So that whether that be the slide cylinder type, which mimics more of that two-cylinder type design where an internal sleeve will actually ride inside of a larger sleeve, and depending on the position of the piston, it would open different ports. Now, I realized that design many years ago, and realized it had its limitations because of the heavier moving components. They'd be limited on how much RPM they could actually spin. Where two-stroke engines can rev, to the sky, they're also restricted to the cross-sectional area of the ports because they have to both deliver air and fuel, and they also have to, get the package out. With motorbikes, the most power per package is kind of the idea. They need to get the most amount of RPM, and being a two-stroke engine, they're getting more power per every revolution of the crankshaft. And normally, utilizing like motocross dirt bikes, the engine has to be very small and light. So, at the RPM ranges within our power band, they can achieve, let's use a 500cc for example. A 500cc motorbike can achieve over 200 horsepower out of the two-stroke design, but the engine can fit basically inside a mini bike. Okay, so the engines are not very large and can produce a lot of horsepower. And with the two-stroke design, they also have less moving components that can fail. So within these videos, we've critiqued and talked about different modifications that you can do to factory designs, whether you're picking something out of the junkyard to transplant in your engine, or if you're just trying to modify what you have. I have a proposition, and it's something that has gone into 30 years of development, to the point where at one point I did have a 3D model, a functioning 3D model. And while I have not been able to basically connect it to a running engine, a cylinder itself, to see what kind of airflow it does and how it acts, I believe it's something that can be contributed to any power plant. So I'm going to introduce my slide window cylinder head design. And if Darren Morgan, once again in the videos here, they said they've worked with all kinds of different companies to basically help get better performance out of their cylinder head, so on and so forth. Now, typically we're using an overhead valve type design, realizing that the air has to travel around the valve and over the valve seats to get into the engine. And Darren, through these last two series, has gone through and described what's the most specific way to be able to get the power in there, the size of the valve in accordance to the bore and stroke ratios, how they all go into it, according to RPM. Now, when you get into the aftermarket, obviously you can choose a handful of different manufacturers of cylinder heads. So let's just use it, Chevy for example. Throughout the last 30 years, there's been at least 15 to 20 different manufacturers. I'm talking, based off the original design from Chevrolet, with different modifications, port design, so on and so forth, even different valve angles, such as the trick flow twisted wedge head that they made for quite a few years. They canted the intake valve back. Now, the whole debate between all the different manufacturers, okay, again, let's stick with the small block family. The 23-degree wedge style combustion chamber, again, some of the canted valves, small block Ford, Boss engines, so on and so forth, they all came in obviously different cubic inches, so on and so forth, and there's always been a debate which manufacturer makes the best small block. Now, because of the designs, the canted valves, it allows the curtain area of the valve to be exposed more to the cylinder to be able to flow more air. So if you're talking about a a 350 Chevy wedge engine compared to a 351 Cleveland, it obviously has some advantages going towards the Ford because of the valve configuration. Now, since all the communication has been basically around the tulip or the nail head type design valve, again, going back 30 years to combine the technology behind two-stroke engines and how two-stroke engine designs can be adapted to a four-stroke engine. Still remaining as a four-stroke engine where there's an intake, compression, power stroke, and then exhaust. Being able to adapt two-stroke engine technology onto a four-stroke engine. And how the aftermarket, again, this would all be within the packaging. How could you come up with a design that if you were to be working with an engine, a V8 engine from the last 60 years, something that could be produced that would be very similar, so you could take the exact same design, go from a small block Chevy to a big block Chevy, and have it work. Obviously, the bolt patterns, the head bolt configurations, and the water passages would all have to line up. But the actual design of the valve is also changed. What can we do to adapt that to where you could design one single cylinder head, one design that could be transplanted between all of the engines, and within the least amount of tooling or design changes could produce more horsepower than a nail head style engine. So today I have a drawing here. You're gonna have to go along with me again. Like I said, I created a three-dimensional object like this. I actually used a clay block, baked the clay, and then I machined the clay block in order to make the cylinder head. Since that point, it is obviously long gone. I'm no longer in the industry trying to develop this. Obviously, making money was more important than trying to develop something and spending money on it. So this is where I'm at today within this design. And like I said, 30 years. So what I'm offering right now, anybody that watches these videos, Darren Morgan is obviously somebody a lot more important than I am, okay? But I believe I have an idea that would prove some of his theories, confirm them, and offer a completely different head design that can be manipulated in so many different ways with just the change of a baseball card. Okay, baseball card size. Sorry, I don't even know how to explain it because it's something so experimental. It's not like anything else. So a baseball card size valve. So say this piece of paper right here, this would be the actual valve to the engine. Obviously a little bit thicker because it would have to be made out of a heavier material, whether it be stainless steel, titanium, or brass. It'd be basically this size. And in order to change the performance of your engine, you just have to swap out the different cards. Okay, now the top picture, what I'm showing here is basically the side profile of the engine. Obviously the cylinder head itself and the valves, the cards, are being actuated by a single cam. Now obviously let's call this the intake and exhaust. So that you could actually place this type of cylinder head on any engine. And depending on the surface face area of the cylinder head, can be machined at different angles with multiple different mounting bolt holes. So even if you're working with a big block Chevy, a cylinder head could be designed where you could incorporate the use of a small block Chevy intake. Different mounting plates could be changed to alter it. So if you're working with a small block Chevy and you'd like to use the high ram, say for something with the similar port placement, you could use something from Buick if that's what you have a hold of. Or if you found out a Buick intake flows better than anything offered for the small block Chevy, with the cylinder head swap and different plate systems, again going to the aftermarket, there's a lot of opportunity for performance gains in this design. Same thing goes with exhaust. You could swap on multiple different exhaust pieces, whether it be cast iron, tubular exhaust system, so on and so forth. But the only change that you would have to make to actually increase the performance level of your engine is the card. Okay? You don't necessarily have to change the cam, because the cam would be designed to function with the greatest amount of efficiency. The least amount of loft, the fastest action, so on and so forth. But the actual exposure, the opening into the cylinder, allowing the air to transfer through, will be determined by the card. Not the size of the card, the opening within the card. Now, I didn't draw this up here, but Darren Morgan in the second episode was speaking of the different designs of intake ports, and he used the small block Chevy as an example. For those of you that understand like the 887s or some of the lower performance models of cylinder heads, they did not have a perfectly rectangular port. They were actually designed similar to this. Even modern day, Charles Servadio, pay attention to this because it's something that you're working on right now. Your Magnum cylinder heads, when you're talking about the pinch point, when you look into the port, even though the entrance of the Magnum cylinder heads is that perfect rectangular shape, symmetrical, okay? Once you go inside of the port, your short turn radius, or your inside cylinder wall side of the port, it has the material at the top, but they've removed it at the bottom, mimicking this shape right here. So the turbulence that's being caused is in this corner. Now that slower area, or that turbulence, causes a speed bump to the air column, and it will force it to change directions. It causes drag. So if you can imagine, let's see here. If you can imagine just taking a rope and swinging it around in a circle. Obviously the pinpoint is where you're holding it in your hand, but the rope will be pulled around that circumference. That's what's basically happening to the air that's traveling through a port. Any low speed areas are causing a drag point to hold it within the motion, and it should cause the air column to actually turn without the mechanical forces of the cylinder head roof. You can alter it without even changing the roof dimensions. Now, this design right here is obviously the port design of the lower performance small block Chevy type cylinder heads. This shape is what's very important. Now, within this cylinder head design, it does not use the nail head design valve, where the air actually has to travel over the exterior of the valve in order to go into the cylinder. The cards themselves have a hole cut inside of the card and shaped similar to the small block Chevy. And the size of this opening within the card is going to vindicate how much air goes into the cylinder, how much shearing effect it has to the fuel. And by modifying it, all you have to change is the card. You can go to an opening that's larger. Okay, allowing more air to go through. You're increasing cross-sectional area without changing the port volume, without changing the cross-sectional port, without having to port the cylinder heads. You can increase the airflow into the engine. Now, because it's using a cylinder head design similar to this, your ports can be humongous, huge. But the only amount of air that's going to be able to follow through or flow through the cylinder head is the amount of air that passes through the cavity that is inside of the actual gate. Okay. Now, like I said, it's introducing that idea, the way that a two-stroke engine is allowed to transfer air from intake ports into the cylinder. The piston moves, the valve is constantly open. As the piston moves, it's exposing a different amount of that intake port. As the piston passes through it, it closes it down. We're just doing it in reverse. Instead of the piston moving to expose the intake port is within the card, and the card moves like so. So in order to change the card, all you would have to do is pull the camshaft, okay? Pull the camshaft out and change your cards. You could have, for instance, Brian Tooley Racing. When you buy a camshaft, they'll have stage 1, stage 2, stage 3, so on and so forth. The aftermarket could create cards that are stage 1, stage 2, stage 3. And depending on the stage you purchase, it is just the opening within the gate that's different. Now, this could also be incorporated with a 4-port type engine. So if you're thinking about a 24 valve type engine, instead of having a nail head valve, you would have 2 gates for each intake port, a left and a right. And the configuration of this opening would just be flip-flopped. Now, because of the increased area on one side of the card, the gate, it's going to introduce airflow into the cylinder from one direction. And as the cam is opening the card, opening this valve, it's exposing more and more of the port. So the design of the opening in the card determines the rate of speed that air can go in, the amount of volume, and keeping velocities up. So this shape can be changed dramatically within different card designs. Now, instead of porting an entire cylinder head to achieve something, isn't it much easier to basically change a card and change the opening within the card? Now, one of the restrictions in a running nail head type design is you cannot open the intake valve because the piston is at top dead center. As the piston starts to move away, the valve can open as long as it has enough room into the head of the piston to clear it. Your valve release, okay? The valve can't open faster than the piston moves away from the combustion chamber. With this card design, the gate design, there's nothing protruding into the combustion chamber. So you could actually open your opening to allow air into the cylinder before the piston actually reaches top dead center, more than what a nail design or overhead valve design could. There's nothing moving into the cylinder. With this design, you're also eliminating rockers. No rockers and no push rods. It's direct between the camshaft and the cards. So at the top of the cards, you could have rollers as wide as they need to be to support and transfer the pressure between the cam lobe into actuating the card. Now, I'm not drawn exactly, okay, I have to do some retention here as far as what I've designed into that, so that if we would like to, again, this is kind of going out to Darren Morgan or anybody that would like to design a cylinder head and put it into production, I'm willing to work with them with absolutely no regard as far as what your legal status is, what I would get out of it, okay? I'm just putting this idea out there to anybody that has the engineering, the computers to be able to design this, and need the input that I've had in my head for 30 years. Creating a cylinder head that we could actually bolt onto an engine and test it to see if this actually works. Now again, I believe it does because it's already being used with 2-stroke engines. You're just adapting the idea of the 2-stroke engine. Instead of the piston controlling the valve opening, the opening is being actuated from a camshaft. Now, in order to trap the gate, the card within the cylinder head, it does have valve springs, and we could use any traditional V8 valve spring. The cylinder head pocket, in order to install the valve springs, be installed at the bottom, pushing up against the card. So the card or the gate is trapped between the valve spring and the camshaft. So when loft is being introduced, again, it shouldn't have to be, because if the camshaft is designed correctly, it's not the camshaft determining the opening of the intake port to the cylinder. It's within the card. So let's say this piece of paper right here is the card, and the camshaft is up here. Your traditional round wound cam springs, or excuse me, valve springs are underneath, controlling the placement of the card within its slot. So as this is opening, as the valve pushes down, it's collapsing the spring, just like in a pushrod engine. This is actually upside down, sorry. So this would be, as the cam opens, it's exposing this smaller portion of the gate, and the farther it opens, exposes a larger area. And to control the actual flow, the only thing you have to change is basically the opening, the rate that it comes in, keeping high velocities, and then you get greater volume by opening wider the opening within the gate. So you can still use traditional camshafts, you could still use traditional springs, but you're replacing everything in between with nothing but a gate, and the gate becomes your intake port. Now, you could still, again, design a cylinder head to be able to adapt any kind of intake system onto it, but the intake port would have to be very large, because it's not the intake port determining how much air is flowing into the engine. It's the opening within the card. So camshaft profiles can be designed for the most efficient action of the card. The only limitations they have is to loft. So even if you have a profile, a very aggressive ramp profile to the cam, that's moving the card extremely fast, just like you would with a nail head valve design. But unless you have the opening that matches the amount of airflow that goes into the engine, you don't need to. You could actually create, again, let me draw this out a little bit more. Instead of lifting the valve further and creating an excessive exhaust, or the cam lobe design, all you change, excuse me, this is upside down again. You just change the opening within the gate. Okay, so this would be for example, say this is a piece of stainless steel, and it's riding in between, it's sandwiched into brass liners, just like a regular valve guide. But instead of them being round, encapsulating around the valve stem itself, it's a flat gate. Okay, so let's say this would be a 1/4 inch thick. Okay, plenty enough to be able to withstand any kind of bending, so on and so forth, and warping, and it would ride in a brass liner within the cylinder head. Now, depending on the head bolt locations, would determine where the ports would actually enter in. But there would be no restriction as far as if there's a push rod going through, like in the Chryslers, there's no limit of how far you can move over without breaking, through the valve guide orifices and so on and so forth. There is no push rods. There's no rockers. It's direct, rollerized, right to a single cam. And that cam actuates both intake and exhaust. You can also alter the gates to be a 1-gate system or a 2-gate system, like a dual overhead cam or a 24 valve type system. Depending on how aggressive you need the airflow to go into the engine is dependent on the opening of each gate. So if you want something to remain very high velocity, you would stay with a smaller opening and just multiply the amount of gates on the cylinder by 2. You're getting the velocity plus the volume. Now within the video, Darren Morgan had mentioned that line of sight. I've mentioned this once again, if you go back to Charles Silver Audio about a year ago. Mentioned that if you take a straight pencil or let's see here. Yeah, let's just say a straight screwdriver. And you put this into the port where the highest velocity occurs. You're going to find the most direct approach from, say, the intake flange to the back of the valve. By altering the curvature or the short turn radius, you can manipulate that flow column within the air. But it's limited. As you go faster and as velocities increase, the harder it is to actually bring it back from being straight. In the second episode, I believe it was released today, Darren Morgan once again brings up his laptop and puts it on there, showing the different straight shot approaches with an intake column, addressing that when the air is traveling straight, the higher velocities are, they can't necessarily make the turn over the short turn radius. So in order to get a straighter approach to the back of the valve, the short turn radius has to be taller. Okay, so if you didn't catch that in the video, if you haven't watched yet, I recommend going and watching it. But again, this is going out to Darren Morgan because he has worked with it and said line of sight. The one thing that we have not tried in the automotive world today is this gate type of system. And it could be incorporated into utilizing the equipment that's already being manufactured. The only thing that has to be created new is the gate and how it's mounted in the cylinder head. That's it. In order to change the performance of your engine without even having to port the cylinder heads themselves, you can unbolt the cam, change the cam. But if the cam is designed with the precise ramp profile that will work in a certain RPM range, it's not going to introduce float. So a very large diameter, say a 75 millimeter cam, that allows the ramp profiles to remain fairly conservative. But even within the action of those slower ramps, the opening within the gate determines how much air transfers over within every action. The opening. Having as large a port as you possibly can, both for the intake and exhaust, it's restricted to the opening within the gate. So if you want to change, say, for an engine that's going to be used on the street and you're jumping up to full drag racing, all you have to do is pull the camshaft. It's the same cam for every engine. Pull out the cards, replace the cards, once again, bolt down the camshaft, and now you got a completely different engine. Instead of having to change the cam to actuate the valves, you're changing the valve, the gate, the opening. So the curtain area is changed without having to increase lift of the valve, of the nail valve. Okay, you're increasing the valve by the opening that's in the gate. Easy enough. Now I have taken this to the extent of designing it around something that would also change duration or movement of the valve at different RPMs. Again, going back to the Honda VTEC, so on and so forth, that the timing of the cams can be advanced or retarded just by centrifugal force. You could incorporate, say, a good example would be the 2.3 liter Ford with the overhead valve. Okay, this was the actual engine that I initiated this design off of. The 4-cylinder 2.3 liter Ford overhead cam engine. Very simplistic. It's belt drive cam. It's not a chain. And the intake and exhaust ports are obviously on the opposite sides of the head. So you have your intake on one side, the exhaust going out the other side. But it's still a wedge-style combustion chamber where the valves are in line directly underneath the cam. What's the difference than if you just put instead of being a tulip valve, changing it to gates? Okay, so this is the format that you could use. You could start by utilizing a Ford 2.3 liter, which are fairly available still to this day. Use it as a prototype to design cylinder heads that will fit on a V8, utilizing the exact same thing. So again, by creating a cylinder head out of the 2.3, you're only making it for 4 cylinders, one camshaft. You could even utilize the camshaft that's already equipped on the from the factory of the 2.3. The only thing you're changing is going from a nail valve to a gate. Your line of sight, instead of the valve actuating and opening and you still see the valve, it's just moving away from you. As the gate opens, your line of sight is being unblocked. You see right through the opening of the gate, right into the cylinder. So now instead of your air transferring over the valve seat or around the valve, it can travel right through the center. Follow me here? So that will address any of the concerns or problems that come with the Apex type intake system. Okay, instead of a valve opening, creating that curtain area on the outsides, the perimeter of the valve, obviously going to a larger valve creates a bigger window. It also causes the valve to be closer to the cylinder walls to restrict flow. If you could take the conventional valve out of a cylinder, a conventional head, and create a gate that would move back and forth with an opening that starts on this side, exposes more of that window of the gate as the gate is pushed up and down by the cam. You can control the velocities throughout the entire power band or entire flow cycle. Okay, if you follow me there. Here'd be another picture of it. Obviously with the smaller, narrow portions of the card, more of the vacuum or lack of vacuum is being exposed to that area. It's going to create a very large signal, a strong signal to create high velocities. And the taper of the opening of the card as it's being opened will be matched to the velocities that can occur within the opening and the travel of the piston down. So as the piston reaches approximately 72 degrees down the cylinder bore, the widest portion, the largest area of the opening in the card is being exposed. Less restriction. You're actually removing the restriction of the valve out of the intake airflow path. So again, instead of these ports having to be, for example, a small block Chevy, instead of using a 230 or 245 cc intake port in order to get the cross-sectional area, you could still utilize a 200 cc intake port, because instead of counting on the entire cross-sectional area and the valve restriction, you're opening the valve. The air doesn't have to go around the valve in order to get in the cylinder. It'd be a straight shot in and out. And it can be built utilizing equipment that is already available. Once again, you could actually take this exact design, create a cylinder head with drop-in cards, okay, that just go in through the top, bolt down the stock Ford 2.3 liter cam to actuate those valves. The only thing you would have to change is the way to retain the gates within the cylinder head. So the valve springs would have to be mounted on the exterior of the cylinder head, or the cylinder head would have to be made bigger to house the actual valve springs. Now, going back to the earlier designs of the 4-stroke engines, you flathead Ford guys, you're going to understand that those valves, in order to access those valves, all you have to do is take off a door. Okay, to change your valve springs, all you have to basically do is open the access door and you can see all the valve springs. You could do the exact same thing with a Ford 2.3 liter, creating a door that actually houses the springs. So in order to change your spring rates or travel compression, You just open the door and it would have retainers. The door itself would be the retainer. There would be no, locks basically to retain the valve from pulling through the keepers. The spring would float in there. There is no keeper. The gate being bolted on would retain the valve, retain the valve springs within the cylinder head directly to the bottom of the gate, just like I've drawn here. So you can still utilize what's available in the from production and install it to actuate the bottom of the gate. The top of the gate is being actioned by any cam out there, so on and so forth. The gate moves up and down, and the amount of airflow and velocities within the intake port are determined by the opening. So anybody, say that you buy, say if this were to be put into production, mass production into a modern automobile, gasoline automobile, an individual wants to modify it, all they have to do is take the cam off, okay, pull the card out, and increase the opening within the card. Replace the card, bolt on the cam, now you have more airflow. Okay, it's easy as that. So hopefully you can kind of get an idea of what I've done here in the last 30 years. This is the idea that sprung up to me going through high school, automobile class, so on and so forth, learning the different type of engines. Well, I'm way over. So again, if there's anybody, explicitly Darren Morgan, that would be interested in designing this masterpiece, okay, taking a different approach to the way the air is being delivered into an engine. These are the basic ideas, okay. I'd give you permission, okay. I'm saying it right here. I don't need to sign any contracts. If you can produce something like this with your adaptations to it, please do. If you want to go even further, because again, I have this drawn out more on graph paper, exactly how this could be accomplished, please contact me. You can find me, okay? Type in my name any place and it'll tell you exactly where I live. Contact anybody in my hometown, they'll give you my address, so on and so forth. This design eliminates the restriction created by the valve. It's opening and removing that valve from airflow. It is creating a window for the air to actually be pulled into a cylinder. It is not restricted by the same things as the overhead valve type engine. It could also be incorporated, once again, even on a flathead design. Realizing the valves are inside the engine block next to the cylinder, and the air has to travel outside the valve over to the cylinder, reverse course to go out the exhaust. You could even replace, so the valve's opening up towards the cylinder head, you could have the gates, cards, moving from the cam valley area, or the center valley area towards the cylinder. The cards do not have to be very long. They could actually be half the height of a push rod, or of the nail valve, reducing the weight that's actually being functioned to. Again, depending on the mating materials of either the guide and the materials that make up the cards, how they're being mated together. The only issue that I've run into within this entire design is how to lubricate that. Now you could obviously introduce oil to the areas between, say, the brass guides and the plates, but there would have to be some restriction from that oil being pulled in with each individual intake pulse. That's the only thing I've run into that I can't necessarily figure out. If it's just gravity and the oil is being introduced at the top of the card or at the top of the gate in the valve guide, the gate guide, and gravity is pulling it down, it can lubricate that entire bracket and just drain into the valve spring area. And then you'd have typical oil pickups, just like in any other engine design, to where it returns back down to the crankcase. Or it's just being supplied above the cam. Say the oil that's being used to lubricate the cam is allowed to drip at the top of the gates be introduced to the card. The seal between the opening of the card and the cylinder head is the only restriction. But I believe learning the ring seal control from rotary engines, I believe this process could be achieved. Instead of having a round piston ring, okay, well, the engine would still have the round piston rings, but instead of having just the contact point between the gate and the valve guide, you could install ring strips like the sides of the rotary piston. It would restrict oil from going past it, but allow the gates to still open up and down. And depending on the angle of those seals, it could direct oil to allow it to lubricate the contact points and then drain back because of gravity back down to the crankcase. So kind of a request, anybody that watches this, if you have any way of putting me in contact with Darren Morgan, or if you'd be even interested in this type of prototype design. Again, I have no patent rights on this design. This is something that's been in my head for 30 years. I put it into a three-dimensional clay block form to see if I could actually make it work. It did. But again, it's not something that I created out of cast iron and was able to actually bolt onto the cylinder head of any engine. So starting out, just a suggestion, starting out with the 2.3 liter Ford. As a base to the prototype, and once you function and design or find out how that works within that design, it can be created in any kind of cylinder head that will bolt to any engine. And it utilizes parts that we already have today within production as far as the valve springs and cams. The prototype is using stuff that we already have. Even the CNC manufacturing of the cylinder head would remain the same. That would also allow you to change the combustion chamber shape. You could go to the Hemi combustion chamber. Air in, air out. Okay, easy enough. And that design could be incorporated even into the same kind of engines that use a dual overhead cam or a 4-valve type system. Depending on how fast you want to keep the velocities and how much volume you need, creating a wider power band within that combination coming from the actual openings within the gate. Easy enough. And you can incorporate different timing because the 2.3 liter overhead cam engine is a direct belt driven engine. You can incorporate that VTEC or altered timing within the cam to open the gates differently. They'd be fixed, so if your intake valve is opening earlier, your exhaust would also be opening earlier. It wouldn't be separate. But that would be introduced just in the technology to lead maybe to a dual overhead cam type system using 4 gates per combustion chamber. Again, you're reducing the restriction provided by a nail head design valve. So again, I do not have the machinery. I do not have access anymore. I did purchase a CNC machine specifically to carry that out. My entire shop was built around the CNC machine. I turned it on once, the system crashed, and I never used it from that point. I never had anybody approach me to use the CNC machine. 20 plus years on a $550,000 investment that only worked once. I attempted to start machining a cylinder head for a 2.3 liter to use the gates. I never finished. So anybody that has the equipment now, the computer data to be able to construct it, please reach out to me if you're interested. Again, Darren Morgan, I would love to work side by side with you. Give me a call and go through this. I can send you more detailed drawings of exactly how it happens. I'd love to be part of it. And I'm not asking for anything out of it. Just acknowledge that was my idea. That's it. I'm not asking for any kind of financial contributions or any rights or anything like that. I'm just there. I'd love to see this. I'd love to see this design incorporated into something. With that, thanks for joining in. It would add an additional, completely additional way of technology of thinking about airflow into a cylinder. I'm going to close it out with this. In the most recent Performance Engine Expo, Darren had mentioned that places like Lockheed Martin, Boeing, the way their intakes are to feed the air into the turbine jet engines, the airflow across the intake pass, so on and so forth. I was there during the design of the F-35 and F-22. I was a security personnel during those prototypes by both Lockheed and Martin. I understand the sharp edges of the design of both of those Generation 6 fighter jets were not only to reflect radar. The sharp points of the air intakes was also the high speed sonic air entering into the engines. And if you realize the F-35, it is the largest turbine engine produced, not power wise, but the actual fins, the turbine itself, is the largest diameter turbine engine created for a fighter craft to this day. It also has the smallest intake ports, but they're a direct line of sight. So I get what he's saying. I know it's there. This is somewhat, I've taken the technology. This was back in the 1990s when Boeing and Lockheed were designing the Generation 6 aircraft. It was precisely the time I was going to school for mechanical engineering in Virginia Tech. It was also precisely when I was going, continuing my education with the automobile industry. It is something that just never came to fruition. I thought about it, created it as much as I possibly could within a clay model. It's never been produced in a metal composition. I'd be very interested in anybody copying this idea. Go right ahead. Okay. I'm sure anybody that's got patent rights, you could design something on there, but it's not an exact. I have the original drawn down, so on and so forth with that. I'm just babbling on. I would love to see something like this happen. Even DV, if you like to, you enjoy retirement, okay? Darren Morgan, any other cylinder head flow specialists, get in contact with me if you would like to go into producing something like this, and we can work together with no strings attached. Have a good one.